All right, so today we're moving on to chapter 9. Okay, and chapter 9 starts talking about, or is about bonding, right? And so we know a little bit about bonding already, but only kind of superficially. We've talked about two different kinds of compounds that contain bonds. From the very beginning, we've been talking about these two different kinds of compounds. Emily, do you think you can read my mind and know what two kinds of compounds we are talking about?
Um, uh, Ionic, maybe.
Ionic is one of them. That's very good. And what's the other one?
Um, is it molecular?
That's right, molecular. All right, so we've been talking about these compounds. I haven't really discussed a lot about the bonding, but indirectly we kind of have, because we say that ionic compounds, the strictest, most strict definition is that they're compounds made of ions. Now, we also usually can recognize them because they contain metals. But remember, something like this is an ionic compound because this is the ammonium ion, right? So again, the strictest definition of ionic compound, made of ions. Usually it's something that has a metal and a non-metal, so it's really easy to identify that way. And when those compounds formed, sodium, for example, and chlorine meet at a restaurant, right? Sodium's big sad story is that it has one extra electron. Chlorine's sad story is that it has one few electrons, right? And so, hopefully this is not a new story to you. I've told you this sort of thing, I think, a variety of times, where sodium gives its electron to chlorine, and the resulting attraction between those charges is what we call an ionic bond, right? So that's our story, an example of ionic compounds that we've talked about. Molecular compounds, we really haven't talked a lot about what's going on between there. We have mentioned that there's a sharing of electrons, and that's why another word for a molecular compound is a covalent compound, meaning that in terms of their valency, their need for electrons, right, is the same, covalent, they're the same. So both carbon and oxygen want to gain electrons, and so they have a sharing going on when we combine electrons like that, or water, another example, right? Molecular and ionic compounds are our two groups that we've kind of introduced and been talking about. And molecular, all are made of nonmetals. Again, no ions involved in that compound. Okay, so we're going to talk a little bit more about this initially, and then about the interactions that are going on in between these ions. And then we're going to talk more about, towards the end of the chapter, the interactions that are going on between our nonmetals and our molecular compounds. So let's start off talking about this chemical reaction between sodium and chlorine. So this chemical reaction here is green chlorine gas in the flask, a little piece of sodium metal at the end of this glass rod. All right, we push the glass rod, or the sodium down onto this sand, bottom bit of sand. The sand is there because of the heat that's generated. It'll crack the glass, and so the sand helps kind of collect some of that heat. Initially nothing happens, but we can activate the reaction by adding a drop of water. The water reacts immediately with the sodium, and then after that generates a little bit of heat, then the reaction between the chlorine and the sodium reacts, and you see that big release of energy, right? That light is electrons rearranging, right? Dropping down, changing from n equals 3 to n equals 2, for example, shifting down and releasing photons of energy, right? Now let's talk about that reaction in terms of what we learned last chapter. Here's a kind of a difficult question, Harry. Let's see if you can see. What does IE stand for in this slide? IE. Thinking about last chapter right at the end there. Any ideas, Harry?
Is that ionization energy.
That's right, ionization energy. Now, this ionization energy, it looks like 495 positive, requires energy, 495. Now, is that energy, is that the energy associated with removing an electron from sodium or giving an electron to sodium, Harry?
I think it was removing.
Removing, that's right. And remember, there's another term that I like to use instead of ionization energy. Ionization energy. I said that that was not a good term because it's, I mean, nobody else in the world agrees with me, so you're going to have to remember ionization energy. But let's see, James, do you remember what I said maybe was a better term for ionization energy? Do you remember from last time we talked?
I'm not sure actually.
All right, I'm going to open up this one to anybody because it's kind of a fringe question. What did I say would be a better name for ionization energy? To better define what it is. Anybody remember? Not a single soul? Here's a hint. It has to do with what kind of ion is being formed in when we were referring to ionization energy.
Is it cationization?
That's right. Remember I said that I wish they would have called it cationization energy because then we would know that ionization energy is the removing of an electron, right? It would be in the name, the title of the energy, right? But alas, we have to just remember that ionization energy is referring to cationization energy. And if we remember cationization energy, then EA, what do you think EA stands for, Catherine? Do you remember?
Oh.
Okay. EA is the opposite of ionization energy. It's E stands for electron. And A, anybody remember that weird word? Katie?
I don't remember.
Okay. EA is the electron affinity of chlorine. All right. So electron affinity, the opposite of ionization energy, is the energy associated with giving an electron to an atom. All right. Now, we hopefully also remember the kind of allegory of the family with many electrons. Removing an electron, what did we say in terms of energy? Landon, can you respond to that? Or do you not have a microphone? Maybe you could type it down below. Oh, look, Landon answered affinity. Good job, Landon. In terms of energy, Landon, you can type it down below for us. In terms of energy, when we remove an electron from an atom, will that require energy, release energy, or it just depends on the electron or the atom that we're removing it from? Well, it depends on the atom in terms of how much energy, but any family will require energy to remove a what's it called? A child from it, right? So we will always bother the family to remove an electron. And remember, successive electron energy or ionization energies will always require energy to remove. Now, what about gaining an electron? Who's next? Nicole. Gaining an electron. What did we say? Do we remember? Does it, in this process, it looks like it what? What does it require or release energy for this step?
It released energy.
The releases energy. Now, do we remember, is that for every atom that it will always release energy to receive an electron? Do you remember?
No. I mean,
Okay.
it doesn't.
What's that?
It doesn't, right?
It doesn't what?
Require or release energy for every atom.
Well, actually, it does. It will always release energy to give an electron to an atom, the first one. And our way to remember that is to say, if somebody came to you and said, hey, look, we have a child, doesn't have a parent, is there any way you could take it? Sure, everybody would take one child, right? Now, That's not true for the second child, for the second electron. The first electron, every atom will take an electron and release energy. But for the second electron and thereafter, it will require energy to, sorry, did I say release? I meant acquire. It will require energy to get a second electron. The first electron will release energy, but the second, third, fourth, and thereafter would be a positive value here, would require energy. Okay. All right. So then, if we look at the ionization energy for sodium, again, it always requires energy to remove a child from its family, to remove an electron from an atom. It always requires energy. We look at the electron affinity for chlorine. Again, it always releases energy if we're just giving one child to a family. But we see that the net energy here is still a positive value. We just saw the chemical reaction, right? We saw that the reaction is exothermic, all right? So why is the reaction exothermic if the ionization energy, if the ionization energy is larger, the ionization energy for sodium is larger than the electron affinity for chlorine? If the net energy change is a positive value, then why is this reaction exothermic? And the answer is because there's more going on. There's more things than just an atom receiving an electron, and an atom releasing an electron. And these are the different, or this is one of the major contributors to this process. And it's called the lattice energy. Because after you form those ions, all right, so down below here, I'm going to draw a picture for us. After we form those ions, so I have some positive ions that are now formed. These atoms all gave up electrons. These atoms all took electrons, right? I have all of these ions. Well, as soon as they attract and find each other, they form a relatively strong bond. And again, this process of taking one thing, combining it with another to form a bonded, that's supposed to be a negative sign, to form a bonded couple, delta H, what do you think? Positive or negative, Precious? Is this process going to release energy or require energy?
Did it release?
It would release energy. That's right, because we're taking these charged particles and we're bringing them together to satisfy each other's charges, all right? So the process of taking a bunch of unbound charged particles and allowing them to form a three-dimensional lattice actually releases quite a bit of energy, all right? Vice versa, if you take a lattice of ions and you try to break them up into their individual entities, right? Ions in this case, that is going to, what do you think, Samantha, require or release energy to take the ions that are all in this lattice and break them up into individual ions or atoms, or ions, positive or negative? Is that going to require or release energy, Samantha?
That release energy?
That actually requires energy, right? If I take this lattice and I try to separate all of the atoms individually, that requires energy. And the list here, this list of lattice energies, shows us how much energy it, in this case, positive. So it must be listing what? The energy that changes when the atoms come together. Or if it's a positive value, is it the energy when the atoms are broken apart? Kim, Taewan, what do you think? Is this positive value the energy when the ions come together? Or is the positive energy associated with the three-dimensional lattice breaking apart?
It requires energy to breaking up.
That's right. It requires energy to break that three-dimensional lattice apart into the individual ions. So, when you look at a table of lattice energy, it won't say this is how much energy is required to break the lattice. It's just going to give you a value. but you have to know what this lattice energy means. This is the energy associated, has to be, because they're all positive, associated with breaking up that lattice. So if we look at this energy, the energy associated with removing an electron from sodium requires energy. The energy associated with giving an electron to chlorine releases energy. And then with the help of the lattice energy, the resulting process is exothermic, a negative 631 kilojoules per mole of sodium and chlorine atoms. All right, so if we look at it in this Born-Haber cycle, we call it, which is kind of an image, a figure to look at the individual steps. Here's the ionization energy, 495.4 of sodium. Here's the electron affinity energy of chlorine. Here's the lattice energy. And there's actually two other components associated with this process. One is the energy necessary to take sodium as a solid and convert it into a gas phase, because the sodium as a solid isn't going to be able to react any of the atoms except for the surface atoms, right? So when chemical reactions occur, if it's not in aqueous conditions where every ion is kind of free, you have to free up those ions by converting them from solid to gas. So that requires a little bit of energy to convert solid to gas. Here, we need to get the chlorine molecules, which are diatomic, and convert them into monatomic atoms. And that requires a little bit of energy. It requires energy to break that chlorine-chlorine bond. After you have individual atoms of chlorine and individual atoms of sodium in their aqueous or their gaseous phase, then the ionization energy of taking the electron from sodium can occur, and the electron affinity of giving the electron to chlorine, and then again the lattice energy showing the overall change from where we start to where we finish being an exothermic reaction. Okay, so when we have our reaction between sodium and chlorine, right? Sodium atom, so sad, has an extra electron. Chlorine, so sad, needs one more electron. They share, an electron is shared, and then the resulting compound is formed. I was just teasing you, right? That's not a true story. These are the true facts of the story, right? Sodium needs to sublime into a gaseous phase. The gaseous sublimation is followed by chlorine molecule breaking up, and then the ionization of sodium, the electron affinity associated with chlorine, and then the lattice energy, right? But isn't that story so much more boring than my story, right? So anyway, that's why I told you that story first, to help us along. But now we can see all of the steps associated with that process. Now, you know, when kids come of age, they have a very difficult question to ask their parents. It makes them feel very uncomfortable. And I'm going to help you with that question, okay? And for those of you who aren't familiar with the question, this is the question that children will sometimes, at some point in your life, ask you, and you have to be ready to answer the question, all right? This is the question. Mommy or Daddy, why is it that sodium always forms a positive charge and chlorine the negative, and not sodium forming the negative charge and chlorine forming the positive charge? They could still come together and form a compound, right? Why is it that sodium always has to give up his electron? Why doesn't chlorine take the electron? Now you could say something like, well, you know, it's really because of their location on the periodic table. Chlorine wants to gain an electron to become like a noble gas configuration. Sodium wants to lose an electron to become like neon. But what if they say, but what if they're stable with their feelings, right? What if they don't care about becoming like an electron configuration? In other words, they want an energy answer, not just some story answer, right? Well, here's the energy answer. Here's what would happen if we decided we wanted to try this process down below, taking sodium and chlorine, removing an electron and giving it to sodium to form that compound. We would still need to sublime the sodium, so there would still be a positive 107. We would still need to break the chlorine bond, positive 121.3. This time, instead of giving an electron to sodium, taking an electron from sodium, we're going to give an electron to sodium. How much energy does it take, Emily, to give an electron to sodium? Can you tell from this slide? How much energy does it take to give an electron to sodium? Does this tell us right here? Can you see that? How much energy does it take to give an electron to sodium? Emily, are you there?
Yeah, sorry.
How much energy does it take to give an electron to sodium?
It would it be negative 53?
That's right. That's right.
Electron affinity.
It releases 53 kilojoules of energy per mole. So instead of going positive 494, we would release 53 kilojoules of energy. And your child might say, aha, see, told you, Dad, that's a lot better than costing 495.4. It could release the 53 kilojoules of energy. And you say, okay. Then let's look at chlorine. How much energy would it take, Harry, for chlorine to release an electron?
For it to release?
To release an electron. To lose
As
an
in
electron.
remove?
Yep.
1,251 kilojoules.
That's right. 1,251. Oh, that's going to kill us, right? So much energy to remove an electron from chlorine. And the forming of the bond would still release this 787 kilojoules of energy. But because it's going to require 1,251 kilojoules to remove an electron from chlorine, then there's no way that sodium is there's no way that sodium is ever going to be able to form a negative charge and have chlorine release that electron, because it just takes too much energy for chlorine to give up an electron. It's okay if we want to give an electron to sodium, that releases energy, but to take an electron from chlorine, that just requires too much energy. All right, so now we can see the specific reason, the step that is energy limiting, right, in terms of performing that sort of chemical reaction there. And this lattice energy associated with the ions coming together, like if I take sodium ions and chloride ions and I bring them together to form sodium chloride three-dimensional lattice, again 787 kilojoules of energy is released for every mole of sodium and chlorine that I bring together to form a mole of sodium chloride. This energy is related to Q1, which is the charge on my particles. So the charge on my sodium atom is a +1, just 1, right? The Q on the second particle, which is a 1 as well. So it doesn't matter what the symbol is there, it's just the number. So it's 1, 1. There's a proportionality constant to convert these charges and distances to energy. But then R is the other variable that determines the energy. So there's the charges and R, which is the distance between the two particles. So the distance between the two particles is governed by the size of the sodium atom, sodium ion in this case, and the chloride ion, right? The size of those two would limit how close those atoms can get to each other. The closer they can get, the smaller this distance, the larger the energy associated with forming that lattice. Okay, so looking at that equation, James Oliver, can you tell me which of these lattice energies do you think would be greater? That of calcium carbonate or potassium bromide? Which one do you think would be have a higher lattice energy, James?
I'm gonna take like a guess and say potassium bromide.
All right. So why are you guessing? Why are you guessing potassium bromide?
Wait, hold on.
So here's our equation.
I think it's potassium bromide because is it because bromide's like farther down the table?
Well, looking at this energy, what is it that governs this energy? What did we say? We got Q1, Q2. What are those things? What are Q1 and Q2?
Oh, the charges on particles?
The charges on the particles. So which one has the greater charges on the particles? The calcium carbonate or the potassium bromide?
Oh, calcium carbonate.
Yeah, the calcium carbonate has the larger charge there. So it's likely that the calcium carbonate is going to have a larger energy here because the charge is larger, right? So here it would be for potassium bromide, it'd be 1 and 1. So 1, we'd have 1 on top, 1 times 1. Here we'd have 2 times 2, so we'd have 4 times 4 on top, right? Now the other factor, we might say, well, potassium and bromine are very small. I don't know, they're not necessarily small, but if we knew that they were very small and their radius was going to be smaller, then it might be, if it was 4 times smaller, it might be small enough to compensate for those extra charges because it's this ratio between charges and how close the ions can get together. But here we would have to probably go with the charge. The charge on the calcium and the carbonate ion is such that it's going to make that energy larger. Okay, good. Now this slide here talks about electron configuration and how we can use our electron configuration to determine what our ions are going to be on our atoms. And we've done this already a little bit, a lot, depending on your perspective. For example, we can look at sodium's electron configuration. And what do you think, Catherine? Number of valence electrons, are we pretty good at that now? How many valence electrons does this electron configuration have?
1.
1. It's this 3s1, right? The larger n value. And so we can identify the kind of ion that would like to be formed simply by recognizing that elements would like to lose their valence electrons. Same with calcium down here. We have electron configuration. 2 electrons, 2 valence electrons. And we can see that calcium would likely form a +2 charge to lose those 2 valence electrons. All right, this octet rule, I don't like to, we just don't spend a lot of time talking about the octet rule because it's good for some things but not good for others. And but the term octet rule stems from this, where we see that in the end, sodium has 1, 2, 3, 4, 5, 6, right? 6 plus 2, 8 electrons in its outer shell when it loses that valence electron, right? Down here, 8 electrons in the outer shell when it loses those 2 valence electrons. That octet rule also works for molecular compounds, and we'll talk about that in the future. But that octet rule, which we didn't initially talk about that in high school chemistry, this is like one of the first things that we talk about when we're trying to explain why atoms do what they do, because it works really well for the representative elements, right? Okay, so if we look at something like gallium, oh no, this isn't the one we want to do. Let's look at this one right here. If we look at something like bismuth, because we've already done some practices, so I think we can skip those ones. And if you are still kind of weak on that, we'll use this as a review. If we look at bismuth, okay, let's bring it up on the periodic table here. Here it is, right? And hopefully, simply by looking at the periodic table, we can see that it has how many valence electrons, Katie? I mean, we can see here in the electron configuration as well, but I think that using the periodic table now, we're pretty good at that. How many valence electrons does bismuth have, Katie?
It has 5.
5. And of those 5, so it's this 6s2 and 6p3. Of those 5, the 6s2 and the 6p3, which of those batches Landon, let's see, can Landon talk to me? I can't remember. Can you talk, Landon? Oh yeah, down below. He's going to answer the question down below. Which one, the 6s2 or the 6p3, has higher energy? This is 6p3. That's right. The 6p3 has higher energy. Okay? So now let's remember how that works. When two sets of electrons have the same n value, and that's the case here, and n is usually our number for identifying energy, right? When two sets of electrons have the same n value, then we can use the L value, and this question will be for you too, Landon. We can use the L value to distinguish between energy. We have S and P. What is the L value associated with S, and what is the L value associated with P, Landon? Remember that? Okay, that was very close. S is actually L equals not 1, but 0, and P is L equals 1. Remember that? So we have, let's a little space over here to the right. Our L equals 0, 1, 2, 3, right? And we have some shorthand for those. The shorthand is that for that, we call these S, P, D, and F. Remember that? All right. Excellent. So the P are higher in energy, or the L equal 1 is higher in energy than L equals 0. Okay, 6p3s then are the highest in energy. And we might not be surprised that bismuth forms a +3 ion by losing those 6p3s, and then it also forms a +5 ion by losing that 6s2. All right? Now, let's look at nickel. Where are we at? Nikki. If we look at nickel, here's its electron configuration. What do we predict maybe would be a feasible ion that this atom, nickel, would form? Any ideas, Nikki? What kind of an ion? A +2?
Yeah.
Yeah, that's right. Nickel will form a +2 charge. And what does it do to form that, Nikki? What does it have to do?
It loses the 4s2
That's right.
It gives
It's 4s2 electrons. Very good. Now, Precious, what is another possible ion that we might think would be formed from nickel? Okay. Any ideas? Should we review this one together? If we remember that we have 4s2, 3d8, right? 4s, 5 orbitals in the 3d, 4s2, 3d8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. If we've already formed the nickel +2 ion, and we have the 4s2, what do you think, Precious, would be the next ion that this nickel might form?
Nickel with +5.
Okay, +5. Very good. +2 and a +5. Now, here's a little bit of a problem. It turns out that nickel doesn't form the +5 very often, but it does form a +3. Precious, can you explain why nickel might form a +3? What it might be doing when it forms a +3? Any ideas?
I have no idea.
No idea. Okay, so what it does is nickel, 4s, and then our 3d. What nickel does is it forms a +3 by losing those 3d electrons, like that. All right, so you get a +2, a +3, and very rarely do you see a +5. But usually you'll see a +2 where it loses these 2 electrons, or a +3. And now that's because, as we said, every time an atom loses an electron, it requires more energy, right? So to release 5 electrons, it requires a lot of energy. It all adds up, right? Each one requires energy. So to remove 5, it requires a lot. All right. So, and that's how it is for these metals, transition metals. Usually we don't find ourselves in a situation where we can make a perfect prediction. Usually we look at the ions and then find an explanation based on the electron configuration why those ions exist. All right? So here's another question that I'm going to have for you here. Zinc atom. All right? Zinc atom, unlike other transition metals, zinc only forms one charge state, only has one kind of ion that it forms. All right? I'm going to break you guys up into groups, and I want you to answer the question, all right, based on our understanding of electron configurations and orbitals. Why does zinc only form one ion, one kind of ion? And might as well answer, what is that charge? Okay, so I'm going to break you up into groups, and you're going to answer this question. Why is it that the zinc only forms one charge, and what is the charge on that ion? Okay, let's see if we got... Oh, it's... All right. Hopefully these will work. Okay, go ahead and go to your groups, and then we'll come back in about a couple minutes.
You are currently the only person.
Well, Harry, are you there?
Yeah. Oh, I'm with you, Doctor.
Yeah, we're waiting for Taiwan.
Okay.
You there, Taiwan?
Yeah, I'm here.
All right, great. What do you guys think?
I did the electron configuration, and right now the suborbitals, the subshells are full. So I think the only ion that can form would be a +2.
Okay, let me see if I can, how do I bring up a,
Green.
Yeah, a little screen that we can write on. Where are my options? How did I do that last time? Somewhere on here. How do I use that as a whiteboard? Clear says multi save using the lock views, write closed captions. Options. No, add actions. There we go. Oh, here it is. Okay, there we go. Okay, so there we go. I can't make a new slide. Ugh. So who can write on it? Who was that? Is that you, Harry?
Yeah, I wrote on it.
How did you write on it?
I just drew it on my phone like this with my mouse.
Well, why don't you draw us the electron configuration, can you?
Yeah. So it's argon, and then there's 4s and 3d. So that would be it's kind of messy, but that's the electron configuration.
That's right. Good.
And I just thought there's only one, if there is one possible, it would be zinc with a +2 charge from the S subshell, because the ones in the D subshell have more energy, so to remove it, you require a lot.
Yeah. And if you tried to remove just one, then you'd be breaking up a full subshell, right?
Right.
Okay. That's right. Very good. Okay. So let's go back to our our big room. Okay, where were we at? Whose turn was it? Was it Katie's? Oh, no, Nikki, Precious, Samantha. Was it Samantha's turn? Samantha, did you guys get to talk about it?
We did.
Great. What did you think? First of all, what is the charge that zinc forms?
Zinc forms a +2 ion.
That's right. It only forms a +2 ion. So why doesn't it form any other ions?
Because the 3D10 shell is full.
That's right. Because the 3D10 shell is all full, there's no other compound it's not going to improve its stability by removing another electron. All right. That was Samantha. Very good. Taiwan, I'm going to give you a hint about this one. Scandium, this element right here, scandium only forms one charge as well. Scandium only forms one charge as well. Do you think you can tell me what kind of a charge that would be? Scandium, and everybody can think about this. It's a little bit of a hard question. It only forms one charge. What do you think, which one would it be? Any ideas, Taewon?
3D10, 3D1 shell.
What charge would it form? Say that again a little bit louder. What would the charge be on the scandium ion?
Just +1.
No. Good try, though. I should have given that as a hint. It only forms one charge, and it's not +1. What do you think, Emily? Want to take a guess?
I'm not sure.
Okay. So let's take a look at its electron or its orbital diagram, okay? Scandium. We're looking at our 4s2 again and our 3d. How many electrons in the 3d, Harry?
1.
Yeah, just one electron. So, scandium, any ideas, Harry? What do you think is the only charge that scandium will form?
I actually thought the same as Taewon because 4S is full and 3D, you just need to remove one for it to be a balanced subshell.
Mm-hmm. That's good thinking. But the answer is actually a +3. It only forms a +3. So what do you think happens, Harry? Why is it that it forms only a +3? What do you think is happening here?
So all the electrons, they are all removed.
That's right. And why is it? Why won't it form a +1, do you think? Where would it like to remove its electron density first?
The 4s2.
That's right. So it wants to remove those. So if anything, it would remove those +2. But if it's going to remove those and leave behind that ugly thing, right? It just has to remove one more, and then it has what when it removes one more?
+3 charge.
Has a +3 charge, and what is left behind? What would be the electron configuration for scandium +3?
Just argon.
That's right, just an argon core, right? So you find a lot of stability if you are exactly like noble gas electron configuration. So what that shows us is scandium and yttrium, they'll only form +3 charges. Actually, there's very few scenarios where there's differences, but that's what you generally see with scandium and yttrium. Okay, very good. So, a little bit of review, a little bit of application of ionization energies, electron affinities. When we get into the Taewon, did you have a question?
No.
Okay, all right. We'll get into doing some more predictions, and then we'll get into molecular compounds. Molecular compounds, how they come together and form bonds, and how we can learn how to draw those compounds and what that means for us. Okay, so tomorrow at noon, my lab section is going to meet, okay? We're going to meet tomorrow at noon because we want to see where you guys are at, all right? Now, I would strongly recommend trying to do a couple of those exercises to be in a position where you could ask questions and understand a little bit about what's going on. So for those of you who are in my lab section, I'll see you at noon. I'll meet tomorrow at noon. If you're not, hopefully you're getting the information you need to from your lab instructor. We have a practice test, a practice exam. Practice exam is open right now, but I'm going to close it tonight at midnight. And that practice exam, I'll reopen it on Tuesday. But what I would really recommend is that you take it as soon as you can with the knowledge that you have and try to see where you're at. And I wouldn't take it with my book or with my neighbor or with the tutor. I would just take it to start off with and see where you're at. And then when you want to take it again later on, you can do that and you can take notes. We'll have multiple times to take it if you want to. But I want you guys to try to take it without any notes to give yourself a good practice and to see where you're at. Okay, if you have questions, you can hang around. If not, I will see you either tomorrow or Wednesday. Any questions?
I had a question.
Yeah.
The practice test, will we have another one?
Maybe. We'll see how time goes. We'll see if...
I mean, not like the practice test, but we've had 3 exams so far. I was wondering if the practice test was leading to another one.
The practice test is trying to get us ready for kind of how we're going to take the final. I don't know exactly how the final is going to be. It depends on a variety of things, one of which the method of proctoring the final. The other is, well, it all kind of relates to the method of proctoring. If we can get the ACS final, so we have access to an ACS online final, but it needs to be proctored a specific way. And we're trying to figure out if our methods will work that way. So it'll probably be just practice exams from now until the final, if that's what you mean.
Okay. It's not going to be at a certain time, right? It's just for a certain day because a lot of people went home and everybody has different time zones now.
Sure.
Okay. And I was wondering about the last thing we talked about for scandium.
Yeah?
So whenever there's an ion that would be formed, will we always start with the largest N value and then work from there?
Almost always. Almost always. We saw a weird exception with nickel, right? Nickel forms a +3 ion where those 3 electrons remove before the calcium and phosphorus or potassium do. But yeah, almost always will the valence electrons leave first.
Even if the subshell is full, like 4s2?
Even if the subshell is what?
Even if the subshell is full?
Which one?
Like for scandium, it's 4s2 3d1, right?
Right.
But the 4s has 2 electrons, so it's full, which means it should be stable.
Oh, I see what you're saying.
Yeah.
Yeah, those are the 2 electrons that'll want to go first generally because they're the highest N value. So yeah, usually our higher N values are the ones that go first.
Then are there any other exceptions like nickel that we need to consider? Or is this like a rule of thumb?
We don't have to really know any of the exceptions. And we'll never really be tested on any of the exceptions. And we don't want to spend time like trying to worry about that. But yes, there are a lot of different weird scenarios that occur because of that. So copper, for example, let me see if I have the copper one up here somewhere. Here's copper. Copper, 4s2, 3d9, right? That's the electron configuration. 3d9, 4s2. Right? Copper forms a +1 ion where you get 4s1 and 3d10. So what happens here is, let's see, is that right? 4s, 3d9, 4s2. So 1 electron. Let's see. What are the correct electron configurations for copper? Oh, sorry. 1 electron here for copper moves from the 4s1 to the 3d, and sorry, from the 4s to the 3d. So copper's electron configuration is actually 3d10 4s1. And when we lose that electron, it comes from, when we lose +2, one comes from the 4s1 and one comes from the 3d10. All right. Those are, again, just exceptions, and it's kind of interesting, but not so much for us, right? And these exceptions have to do with kind of this row right here. So
Okay.
zinc, I mean, I don't know if you call that an exception. Zinc's not really an exception. It just doesn't have any other ions to form. But copper finds itself in a situation where that energy for that second electron is very similar to that 9th or 10th electron in the 3D. And so it will be removed. In fact, copper 1 is a relatively stable ion with 3d10, 4s0. Right? So
Yeah.
what's happened there is one electron has left the 4s, and the second electron doesn't stay in the 4s, but it transfers out to the 3d. Anyway, there's a handful of other wine, just a few more in there, but the kinds of things that will generally be required to understand is, given an electron configuration, how would the given a charge, how would our electron configuration or our orbital diagram be changed, right?